Hi everyone, my name is Deepankar Chanda and I will present our work on semantic-aware image inpainting. Distortions in images may arise during the process of acquisition or due to deterioration, masking, or image editing. Image inpainting is the task of reconstructing missing regions in these distorted images. Its applications include restoration, object removal, novel view synthesis, and compression, among several others. To effectively complete a masked region, an inpainting approach should understand the scene context, recover the semantic regions occluded by the mask, and fill them in with plausible textures. Image inpainting is an actively and widely studied area. Modern techniques for image inpainting use a learning-based approach, where they extract image features from deep networks to learn context and locate plausible features to fill missing content. But these techniques simultaneously learn scene semantics and synthesize texture, and so are unable to properly recover structure corresponding to the masked objects. Thus, they produce inconsistent textures and shape. A few approaches try to address this issue by using edges to provide structural information. However, they do not provide semantic context and thus have texture and color artifacts. Broadly, our idea is to separate the task of semantic scene understanding and texture synthesis to make it easier for the system to learn the inpainting process. Specifically, we first estimate the semantic map in the masked regions, then provide this information to the inpainting network to effectively synthesize the appropriate textures. Some other methods also explicitly use semantic information. Song et al. Proposed to guide the inpainting network using a semantic segmentation map. However, they failed to utilize this semantic information effectively. Liao et al. Also proposed to use the semantic information. However, their approach independently predicts the semantic map and image content at a given resolution. This may cause a mismatch between the semantic label and the image content at a given location. To summarize our contributions, we propose to effectively utilize the semantic information through a conditional semantic-aware feature modulation to generate high-quality inpainting results. We introduce a dual discriminator framework which uses image and semantic context to generate visually pleasing results. We demonstrate an extension of the technique to allow user interactivity. We now overview our system that addresses better texture generation and semantic coherency. From a given masked image, we first estimate a completed semantic map. This completed map is then fed to an image inpainting system, which fills the corresponding missing regions in the image to obtain the complete result. We first illustrate the image inpainting system. Note that here we assume the complete semantic map is available to us. Later, we explain its estimation. We use a generative adversarial network to reconstruct the missing portions of the image. The generator takes the masked image and the mask as input. It is composed of an encoder and a decoder. The encoder imputes missing values, while the decoder uses adaptive modulation to effectively utilize semantic information and reconstruct the image using the semantic map. The segmentation map is fed into the transformation CNN, which computes class representations across multiple resolutions. These are used to compute parameters gamma and beta, which are used in the decoder to condition the input image features. The generator then produces the output synthesized image. We now demonstrate the effect of incorporating the semantic information through feature modulation through this example. As you can see, naively concatenating the semantic map with the input exhibits discoloration and poor intrasemantic texture. In contrast, by incorporating the semantic map through feature modulation, we produce consistent zebra stripes. Here again is the naive approach versus ours. In order to enhance the quality of the final result, we train using two discriminators. The inpainted image and the mask is supplied to the input consistency discriminator, which forces the generator to produce results that blend with the input masked image. The generated image, along with the semantic map, is provided to the semantic consistency discriminator, which ensures that the generator can associate feature and texture from the image to the semantic labels. Our optimization objective includes the adversarial loss, a discriminator feature loss, a perceptual loss, and L1 loss to improve the quality of the inpainted result. We'll now see the impact of using the dual discriminator framework. The generator produces blurry texture if a single discriminator is used, where both the semantic map and the mask are concatenated to the input. If only the input consistency discriminator is used, while the generated content blends with the inpainted image, we see that the interior of the mask has texture and color artifacts. On the flip side, if only the semantic consistency discriminator is used, the texture is captured well throughout the entirety of the masked region, but we see the seams of the mask. Our complete result is able to resolve these issues. That completes the description of the image inpainting system. We now describe how to estimate the complete semantic map. First, we use a pre-trained off-the-shelf network to generate an incomplete semantic map for the masked image. We then use a GAN to reconstruct the missing semantic labels and generate a complete semantic map. We use an adversarial objective for optimization, and to reduce noise in the predicted labels, we incorporate the total variation loss. We train our system in a two-phase manner. In phase 1, the label inpainting network and the image inpainting network are trained independently. In phase 2, we fuse the models and jointly train them in order to enhance the quality of the results. That finishes the description of our approach. Now we'll see some results. First, we show a quantitative comparison of each component of our method. We include a comparison across 3 perceptual metrics. A lower FID and LPIP score is better, while for SSIM, a higher score is better. When either only the input consistency or semantic consistency discriminator are used, we see lower perceptual quality scores. The single discriminator takes as input the image, mask, and the semantic map. However, it too performs poorly. The naive generator has significantly worse perceptual metrics. As shown through the earlier visual comparison, our complete system significantly improves the results. We now compare our results against 4 other approaches. We compare against Adobe Photoshop's Content-Aware Fill, Edge Connect by Nazeri et al., Deepfill V2 by Yu et al., and ProFill by Zeng et al. We first show a quantitative comparison against other methods. As can be seen from the table, our method performs well across all perceptual metrics. Next, we'll see some visual comparisons. First, we show an example of image restoration. For each competing approach, we show our results immediately after for better comparison. We also toggle between results to better highlight the differences. We show a comparison against Photoshop, which is unable to understand scene context. In comparison, here's ours. Edge Connect has severe texture leakage. Deepfill V2 has color artifacts. ProFill also has texture and color artifacts at the arm and head. Now, we show an example of object removal. We remove the fold. Like before, Photoshop cannot understand scene context and hence produces inconsistent results. Here is our approach. In contrast, it's able to fuse the legs of the horse with the torso. Edge Connect has severe blurring. Deepfill V2 has severe texture artifacts. Profile does not properly connect the legs of the horse to the torso. Next, we show an example of user interaction. In this example, the user manually edits the estimated semantic map to obtain the desired results. Although our automatically generated results are reasonable, with additional user guidance where the user manually edits the semantic map, our method is able to improve the shape of the legs and the stripe patterns. In conclusion, we effectively incorporate semantic information through semantic-aware modulation. We generate high-quality results by training with dual discriminators, the input consistency discriminator and the semantic consistency discriminator. We demonstrate a practical user interaction method. Thank you. I will now take any questions.